Okay, let's talk estimating sums. So this is called the alternating series estimation theorem. So within the statement of the theorem, we're going to introduce some terminology. This isn't new, but let's say S, we don't talk about it that much. Let's say S is the sum of a convergent alternating series. In this case, S equals the sum n equals 1 to infinity, negative 1 to the n minus 1 bn. So suppose that's the sum of the alternating series. And what is this saying? This is just a restatement of the condition that bn decreases, right? And I put a less than or equal to here by the 0, but it's not very interesting if it's actually equal to 0. So you can change that to a strictly less than if you want. So that's just saying, oh, the bn are bigger than 0. That set of inequalities is just saying the bn are bigger than 0, and bn plus 1 is less than or equal to bn, which means it's decreasing. So here's the conclusion. You can say that the absolute value of S minus the nth term, or the nth partial sum rather, S minus Sn, the distance between S and Sn, the difference between them absolute value-wise, is actually going to be less than or equal to bn plus 1. And before I even attempt to show you why this is true, you have to understand what it's saying. So do you remember what Sn is? Sn is not the same as S. S would be the sum of all the terms of the infinite series if that were possible to do. In reality, it's not possible to sum an infinite number of terms, is it? So the best we can do is we can estimate S, the sum of all the terms in the series, with the nth partial sum, right, and make n big. So Sn stands for the sum of the first n terms of the series, a1 plus a2 plus a3 plus ... all the way up to an. In the shorthand lingo we've developed, it would be the sum. We have to change it to I equals 1 to make the upper limit n ai. And remember, we talked briefly about the idea that we can use Sn to estimate S, right? Assuming that the series converges. So what are we saying here? With an alternating series, we're saying that the error, you can think of S minus Sn, the difference between the actual sum and the nth partial sum, as the error in using Sn to estimate S, right? That's the error. And in fact, you could include the absolute value in that error so that we don't have to deal with negative numbers here, possibly. So you could think of that whole thing as the error in using Sn to estimate S. Does that make sense? So we're subtracting the if we could, right? We don't know S, so we can't actually do this, but we can conceptualize it. If we did know S, okay, let me put it this way. We don't necessarily know S. Sometimes we do know S. But if we did know S, we could characterize the error in using Sn to calculate S by that formula. Does that make sense? What we're saying here, incredibly enough, is that that error is less than the n plus first term of the series, without the negative in front of it if it's there. So it's less than bn plus 1. So what is this saying? I mean, it looks confusing strictly because of the notation, but in practice, once you understand it, it's easy to apply. What it's saying is you could add the first n terms of the series. That's this, right? And be within bn plus 1 of the actual answer. And as you'll see in the following example, it's actually easy to calculate this. In fact, before I prove this to you, let's do an example, because I think that'll help you understand what it's saying. So let's see. It says find the sum of the series n equals 1 to infinity, negative 1 to the n minus 1 divided by n to the fourth. We want it correct to within 2 decimal places. So 2 decimal places, what is that really saying? We want the sum, so our estimate is Sn, and we want that difference to be less than, well, if we get it to be less than 0.01, we're in. Because then the first 2 digits will be correct. All right? Does that make sense? Up to rounding error, I suppose. Okay, so that's what we want. And what the alternating series estimation theorem says, okay, so ASET for short, alternating series estimation theorem, that says that this error, S minus Sn, is less than or equal to Bn plus 1. So all we have to do is find the first term of given by the formula for Bn that's less than 0.01, and we'll sum the terms that come before that. That's what the theorem says. And if you still don't understand it, don't worry. We're going to do it right now. So let's write out the first several terms. Okay, look at the series. By the way, what's Bn? 1 over n to the 4th. That's really, when you write out the terms of the series, you just need to think about what Bn is, and then make it alternate accordingly. So the first term, because it's -1 to the n minus 1, and n starts at 1, is the first term going to be positive or negative? Positive. Because, for the first term, you plug in a 1 right here for n, you get -1 to the 0 power, which is 1. So once you determine that, how it alternates, whether the first term alternates or is negative or not, then you just use 1 over n to the 4th to figure out what each term is and make it alternate correctly. So let's write out the first several terms. So you could say that the sum from n equals 1 to infinity, -1 to the n minus 1 over n to the 4th, okay, I have to use a wavy equal sign here because I'm not going to get to infinity, is approximately, okay, what do you get for the first term when you plug in 1? For the first term of the series, which you can use this to calculate, what do you get? Just 1 over, positive 1 over 1 to the 4th, which is 1. And then the next term has to be minus. And you plug in 2 to get the next term. So what's that going to be? 1/16. And then the next term will be positive, and you're going to plug in 3. So what do you get there? Plus 1 over 81, or 3 to the 4th, minus 1 over, we plugged in 3, let's plug in 4. Well, maybe you don't know what that is, so what could you plug in? You could just write it like that, right? And then what's the next term going to be? 1 over, so we plugged in 1, 2, 3 into this formula, right? And then we made it alternate appropriately. 4, and then it's going to be what? 1 over 5 to the 4th. Let's go one more. You guys tell me. What's the next term? There you go. And it keeps going. If I put in a plus ... then it would be exactly equal, right? So what we want to do, let's try 1 over 6 to the 4th. Now, if we want to be within 0.01, we better make sure whatever term we check has 2 zeros after the decimal, right? Because whatever that number is will be less than 0.01, right? So we need the Bn plus 1 to be less than 0.01. But that means it's going to be a number like with two zeros in front of, or right after the decimal. So you can run it through your calculator, but I'll also illustrate it with my calculator. So 1 divided by 6 to the, 4th power, like that. Okay, what does that equal? 7.7 e to the -4, what does that mean? Or e -4? So 7.716 times 10 to the -4, right? So how many zeros are in front of that first 7 then? 3. Okay. Well, let's go back to 1 over 5 to the fourth and see what that gets us. Well, so the idea here is you want to use as little computing power as possible to make the estimation here. So you want the first bn plus 1 that satisfies the condition. Okay? Yeah, you could go out to the 1,000th term and be pretty sure you're right, but you're saving computer power. You want the first one that satisfies the condition. So what is 1 over 5 to the fourth equal? 1 divided by 5 to the fourth power. Yeah, so that works also, doesn't it? What about 1 over 4 to the fourth? 0.0039. We just need it less than 0.01, right? So we're still okay right there. What about 1 over, that was 1 over 4 to the fourth. What about 1 over 81? That's not going to work, is it? Okay, so that means that our bn plus 1 is right here. This is the first one that's satisfied. 1 over 4 to the fourth. This guy is less than, it's the first term in the series less than the required error. Does that make sense? Everybody see that? That's the 0.0039065 number. Okay. What the alternating series estimation theorem tells, so this is less than our error. So we were given our error. This is our error. Okay. Or that's what we want, our actual error, this guy, to be less than. So technically this guy's the error, and we want this guy to be less than this number. Okay, this is the first number that satisfies it, but what the alternating series estimation theorem then says is, oh, okay, then the Sn we need to take is actually going to be, it's going to be n-wise 1 less than the one that got you this term. So this n was 4. Oh, so we only need to take S3 to be within the required error. So in other words, all you have to do is add up the terms that come before the one that satisfies the required error, or error requirement, rather. And you add those terms, and you're guaranteed, in this case, that S3 then satisfies that requirement. So has anybody done it yet? Has anybody summed these first 3 terms? So this is about 0.95 right here. So we'll say this. So let's everybody check just to make sure. So S3 is equal to 1 minus 1/16 plus 1 over 81, which is equal to, I don't know, you guys tell me. You said 0.95 to the second decimal place? Okay. So I'll make that a wavy equal sign right there. Does everybody agree with that? We have more than one. Not that I don't trust you, it's just if we have more than one person doing it, we're likely to be right if we get the same answer. Okay? So that's it. That's the alternating series estimation theorem. Oh, one thing I should point out is I didn't actually prove that this converges by alternating series test. I'm leaving that to you guys, but it's one of the basic ones.